Welcome to Cloud Native Network Functions with a Network Service Mesh demonstration by PANTHEON.tech. Visit our new page cnf.io for more information on available CNFs. In this video, we demonstrate the capabilities of several CNFs developed at PANTHEON.tech, such as DHCP, Net44, IDS, and Netmon. These CNFs are running on top of a Kubernetes cluster, deployed with Calico CNI for the management of network connections and with Network Service Mesh, or NSM for short, for high-performance data plane connectivity. The demo simulates a vCPE use case in which a client from a private customer IPv4 network, here represented as the demo client virtual machine, is dynamically and on-demand provided with network services such as dynamic host configuration, address translation, port redirection, intrusion detection or prevention, and access control. Each network function is implemented as a separate, lightweight, cloud-native network function, or CNF for short, managed by a control plane agent built using the Legato framework. Data plane network connectivity between CNFs is provided by the Network Service Mesh, with additional high-performance interfaces such as user space MEMIF or kernel space VPP Based TAP. 4 virtual machines have been provisioned using Vagrant. 2 virtual machines are used to run a Kubernetes cluster with 1 master and 1 worker node. The worker node is connected to a demo client virtual machine representing the customer inside a private IPv4 network, whereas the master node is connected to a demo gateway virtual machine used as a gateway towards external public networks. The interface of the demo client virtual machine and the default route are not initially configured, and thus the client is not able to access the gateway and the public networks beyond. We start with only the Network Service Mesh deployed, which will provide a high-performance data plane connectivity between our CNFs. For this demonstration, we have already prepared a set of Kubernetes manifest files that define all the CNFs and resources they need to build the CNF network of our vCPE use case. We will now go through and deploy each manifest while explaining the key parts of its configuration. The order of which the resources are deployed is important, in particular the CNF interfaces, to ensure that NSM endpoints are registered before NSM clients attempt to connect to them. First, notice that the configuration is defined for CNFs as Kubernetes Custom Resources, or CRD for short. The specification of these resource lists defines individual configuration items, such as interfaces defined as NSM endpoints or NSM clients, routes, cross-connects, or CNF-specific configuration attributes. As a first step, we have to deploy the controller for this CRD. The controller will pass the configuration into the control plane agents of corresponding CNFs through the etc data store, which is also deployed by this manifest. Next, we begin building the CNF network for the vCPE use case, starting with network connections. The network topology is described to NSM through the Network Service CRD. The specification consists of a set of routes matching CNF pod labels. For our use case, we define the default route to connect the physical interface of the client and the CNF DHCP into the L2 switch CNF. The following routes then build a chain of CNFs, starting with the switch, continuing with the CNF span, CNF Net44, CNF ACL, CNF IDS, and ending with the physical interface connecting the gateway with the cluster. Additionally, there is a route connecting CNF span with CNF Netmon, used to send mirrored traffic for analysis and visualization. The first CNF to be deployed provides access to the physical interface, connecting the cluster with the gateway. The CNF is based on VPP and uses DPDK for high-performance packet acquisition and processing. The Network Service Mesh is minimalistic in its design. Even access to physical interfaces and L2 switches has to be implemented through CNFs. The readiness of the interface can be verified using the VPP command line interface. Next, we deploy CNF IDS, running snort, to block any malicious activity coming from outside towards our private IPv4 network. For CNF IDS, we have developed a DEC MEMF library which allows to connect Snort with other CNFs over high-performance, user space-only MEMF interfaces. To simplify this demonstration, only two rules were configured for Snort. One, alerting when the Google public DNS service is used, and the other preventing the client from using Cloudflare DNS altogether. A very simple, yet high-performance firewall is implemented using VPP ACLs in form of the CNF ACL. The rules defined for this demonstration prevent hosts from public networks to access our client on well-known ports, such as HTTP port 80. Next, a very critical component is the CNF NAT44, providing IPv4 network address translation necessary for the client to be able to communicate with hosts from public networks. It will be deployed in between the L2 network segments of the client and the gateway. In the next step, we deploy a Redis server, which is used as the data store by traffic analyzer of CNF Netmon. Netmon stands for Network Monitoring. The CNF runs ntopNG to monitor and present statistics about the traffic passing through our CNF network. All passing traffic between the client and the gateway is mirrored into CNF Netmon by the span cloud native function, which we will deploy in the first step. As we continue towards the client, the next component to deploy is a VPP based L2 switch that will connect the physical interface of the client and CNF DHCP under one bridge domain. Next, we apply the manifest of DHCP Cloud Native function. DHCP is configured with a range of 100 IP addresses ready for dynamic allocation, although for this demonstration, only one will be needed for our client. Finally, similarly to the physical interface of the gateway, a VPP and DPDK based CNF is used to provide access to the physical interface, connecting the client with the cluster. As we can see, all the CNFs have been successfully deployed and are already running. Now, let's demonstrate the services provided by CNFs in action. First, we go back to the demo client virtual machine to verify and confirm that the client has been assigned the first free IP address from the DHCP IP pool. Our DHCP Cloud Native function also configured the client to use the IP address of the NAT44 CNF as the default gateway. We will now test the reachability between the client and the outside world by sending ICMP echo requests towards the Google public DNS. Meanwhile, we should observe on the demo gateway virtual machine that the ICMP packets are source-nated by the NAT44 Cloud Native function. All traffic that flows between the client and the gateway is mirrored using the span Cloud Native function into ntopNG based CNF Netmon for traffic analysis and visualization. The web user interface of the Netmon Cloud Native function is exposed via Node port service, which in this Vagrant based demonstration is further port forwarded into the host on the port 3000. Web UI allows administrators to observe visualization of the network traffic in real time, display all active flows, lists all communicating hosts, and many more. Circling back to our demo client, we will request port forwarding for the port 8000 from our NAT44 Cloud Native function using the Port Control Protocol, or PCP for short. Using netcat, we start listening on the forwarded port 8000. With the port now forwarded, it should be possible to connect to the server from our demo gateway. Coming up, we will request redirection from an external port 9000 to the local port 9001 using the Internet Gateway Device Protocol from the UPnP protocol suite, also supported by our CNF NAT44. We will use netcat again to start server listening on the local side of the redirected port. It should now be possible to connect to the server for the demo gateway using the aforementioned redirected port. The actions of port forwarding or redirection are implemented using the net plugin from VPP. Active port mappings can be displayed using VPP command line interface. Next, we will request port forwarding for the HTTP port 80. Remember, however, that the access list CNF deployed next to CNF net44 has been configured to prevent access to well-known ports. Accessing the client on the HTTP port from outside should be blocked, as we will now confirm. Lastly, we will demonstrate our snort-based intrusion detection and prevention CNF. In our simplified demo, snort has been configured with only two rules. 1. Triggering alerts whenever a packet is received from the Google public DNS, and the other blocking any responses from the Cloudflare public DNS, thus preventing the client from using this DNS service altogether. Each echo reply received from Google DNS as a response to echo requests sent from the client triggers a snort alert, which is processed and pretty-printed to standard out of the CNF IDS by Barnyard 2. Similarly, but with different actions and outcomes, each echo reply received from Cloudflare DNS as a response to echo requests sent from the client is dropped by snort, and the event information is processed and pretty-printed to standard out CNF IDS by Barnyard 2. This concludes our demonstration of PANTHEON.tech CNFs interconnected using Network Service Mesh. Thank you for watching, and make sure to check out our new website cdnf.io for a list of available PANTHEON.tech developed cloud-native functions.